video for investigation 2B, which is called the vertical atmosphere. And this is a very important investigation. So I'm just going to say that at the outset that this is an investigation that, for me, it's very important that you understand the content. And so if you find anything about this investigation challenging, then make sure that you watch this video a second time or a third time, or just go to those parts of the video that you need to watch a little bit more to make sure that you're feeling comfortable with the content, because we're going to go into some content that may be a little bit more challenging for some of you, and that challenging content is going to come up again and again as we move through this session. So just be aware of that I'm thinking that this is important and that you need to spend some time on it. Okay, so having said that, I'm going to just say a little bit more before I dive into the actual content. And that is that this third dimension of the atmosphere, this vertical dimension, is incredibly important. For those of you who have never really studied the weather before, the weather for you most likely is just something that happens right down here at the Earth's surface. So you may see clouds in the sky and you know that the wind is blowing, but the weather is something that we experience just right down here, right at the surface. But in fact, what governs what's happening down here at the surface is occurring above our heads. And so it's very, very important that we understand not just how the atmosphere is moving above our heads, but what causes atmospheric motions, the winds above our head. We're going to talk about forces later on in the session that cause the air to move, and ultimately how those movements determine at least the locations of highs and lows, and maybe a little bit of their movement down here at the surface. Just to know for you that this third dimension is really, really important. Meteorologists spend a lot of time studying the atmosphere and the vertical every day when they're forecasting the weather. And so we're just going to touch on it here in this investigation and then touch on it a couple of more times as we move through the session. So let's get started on our PowerPoint and let's talk about some of these initial details. All right, so first of all, I want to talk about how both pressure and temperature vary in the vertical. And this particular graph, which is figure 2B1, is going to really focus on the temperature. And if you take a look at temperature and this red line right here, this is the vertical temperature profile that we see in general. This is kind of idealized in the atmosphere. And what you'll notice is that as you go up from the surface, and this may surprise a few of you, is that the temperature doesn't always just decrease with height. You go up a certain level, and then the temperature actually steadies out, and it's constant for a while. And then it increases, and then it decreases, and increases, and steadies, and so on. The point is that temperature varies pretty strongly with height, and it's not just a decrease. So we have these distinct levels of decrease, increase, and where the temperature is actually fairly constant with increasing height. Now, I'll come back to this because this is really about what figure 2B1 is about in a moment. But before I do that, I want to talk about pressure as well, because we've spoken about pressure, we've talked about pressure at the surface a lot so far, and we will eventually, not in the distant future, just in another slide or two, start talking about pressure in the vertical as well. Pressure in the vertical, unlike temperature, is actually a lot simpler. Pressure always decreases with height. It never increases with height. It's never constant with height. Pressure always decreases with height. Remember, pressure is a function, or it's a measure of weight. We have weight, the atmosphere has weight. So imagine that you're standing on a scale and you weigh 120 pounds. So 120 pounds is your entire weight from top to bottom. Now, if you're able to actually take the scale that you're standing on and lift it through your body, what you would see is that as the scale is moving upward through your body, your weight is decreasing. It's always decreasing. And if you move that scale all the way up, it'll ultimately equal zero when it's sitting on the top of your head. Now, the reason for that is because a scale, just like a barometer, just like a scale, is only able to measure the weight above it. So when you're standing on the scale, you're measuring your entire weight from head to toe. And as you move that scale up through your body, the scale is only able to measure the weight that is above it. And so as that scale moves upward through your body, your weight will always decrease right up until that point where the scale is sitting on top of your head and you weigh absolutely nothing. So the fact of the matter is that your weight, your actual weight, is always going to vary from whatever it is you weigh when you're standing on the scale all the way down to 0 when the scale's sitting on the top of your head. So that's really nice for people who might be a little bit weight conscious, because you can lie and still be telling the truth. If you feel that you'd like to lose a little bit of weight and you have an ideal weight, you weigh that amount already. It's just an issue of where it is that you weigh that amount. So if you want to weigh less than you weigh, you do. So you can always feel good about yourself. So just understand, pressure, weight always decreases with height. All right, now let's go back to our figure 2b1, because I did digress, but pressure is important, and it's important that you understand that it always decreases with height. Now, when we're talking about temperature, you'll see just from the wording on this diagram that we have words that end with either sphere or pause. Now, if we're in a portion of the atmosphere, as we go up through the atmosphere that is in a sphere, that means that the temperature is either increasing or decreasing with increasing height. If we're in a pause, that means that the vertical temperature change as we go up is close to 0. So let's start at the bottom and work our way up. So the bottommost layer, the layer in which we live, is called the troposphere. And the troposphere extends up to about 11 or 12 kilometers, about 7 miles or so. And what you'll see is that in the troposphere, temperatures in general, not exclusively, but in general, decrease with increasing height. When we get to the top of the troposphere, we will enter a layer where temperatures are relatively constant with increasing height, and that is the tropopause. Tropopause. At the top of the tropopause, we will then enter a layer as we continue to go up where temperatures increase with height, and this is the stratosphere. Now, before I move up beyond the stratosphere, I just want to say that, again, the troposphere is where we live. The vast majority of the weather that we're going to talk about in our class resides in the troposphere. Almost every cloud exists in the troposphere. We have some clouds that are actually able to poke up into the tropopause, and we have some pretty special clouds that actually exist in the stratosphere, but they do not produce precipitation at all. So we're going to really focus, once we get past this investigation, exclusively on the troposphere, and maybe not exclusively. We may talk very briefly, just very briefly, about the tropopause, but 95 to 99% of our class is going to reside in the troposphere after this video. So again, moving to the stratosphere, if we move up from the stratosphere, we will hit a shallow layer called the stratopause, where temperatures again are relatively uniform or constant with increasing altitude. And then we'll enter our next layer where temperature changes with height. This is the mesosphere. And again, temperatures in the mesosphere, like the troposphere, are going to decrease with height. The mesosphere is the coldest layer of the atmosphere. And you can see the altitudes at which these layers are located, by the way, by just taking a look at the y-axis. We have a mesopause above the mesosphere, and then for our purposes, when we're talking about the weather, the highest layer in the atmosphere is the thermosphere, where temperature actually increases with height. Now, in reality, the pressure of the atmosphere, by the time we get to the thermosphere, in other words, the weight of the atmosphere up there is much, much less than a millibar. It's way below 1 millibar. So there is some air up there, and there isn't much, but it's very, very hot if you can observe it. Just one last thing, and again, we're not going to really focus on this in our class at all. So basically below the mesopause, you'll see we're in the homosphere. That means that the constituent components, the mix of atoms and molecules in the air, is uniform. It's homogeneous. Once you get above the mesopause and into the thermosphere, then you enter a layer that is the heterosphere. So in fact, what you'll see is the concentrations of oxygen and nitrogen and so on are not uniform. They're not continuous. And in fact, you'll see that because of the intense radiation that actually comes in at the top of the atmosphere that's filtered out in the thermosphere, that some of the atoms and molecules are actually broken apart and they ionize. So you'll have ionized atoms floating around in the thermosphere. We're not going to really talk about the thermosphere at all in our class. So again, like I said, 95 to 99% of what we do is in the troposphere. The remaining little bit, if we talk about it at all, will be in the tropopause. All right, then let's move on. And we're going to start talking about our pressure and temperature variations together now. And we're going to look at a diagram. This is where I really want you to pay attention because we're going to talk about this thing called Stüve diagrams. And we're going to see Stüve diagrams throughout this class from here on out. And we use Stüve diagrams basically to take a look at the vertical temperature profile of the atmosphere in the troposphere and maybe the lower part of the tropopause. And we're going to take a look at how temperature varies in the vertical as a function for this first little bit as a function of altitude, but really after we get through today as a function of pressure. So what you're going to be asked to do first of all is to plot a couple of points on the Stüve diagram. So you're going to be given 3 altitudes. One is just going to be 0, so you're at sea level. The other is going to be 11 kilometers above sea level, and the third is going to be 16 kilometers above sea level. And you're going to be given 3 temperatures in degrees Celsius. And you're going to be asked to plot these 3 points. Now, some of you will have no problem with this. A few of you probably have not taken any sort of math or science course in a couple of decades, and you're in eCampus and you're taking this science class and you're beginning to sweat a little bit. So let me just remind you that when you plot points on an XY diagram, every point has an X value and every point has a Y value. So every point has an X and a Y value. So for example, when you plot this lowest altitude, this 0 kilometer, and this is by the way called the standard atmosphere, but I'll get back to that in a moment. So I want to actually put this dot on the diagram. And there it is. So what you'll see if you take a look at this dot, you'll see the actual altitude if you just go over to the y-axis. And here it is at 0 kilometers. So this point has an altitude. The point also has a temperature. And all you do to get the temperature is go down to the x-axis from the point. And here it is 15 degrees. So this point has both an altitude of 0 and a temperature of 15. So when you plot the points at 11 kilometers and 16 kilometers, you're going to come over here to 11 kilometers, and then you're just going to basically take your cursor, and you're going to go out to minus 56.5, which is going to be right around here. So here is our point. Oh, here's our 11 kilometers, minus 56.5. So again, here's 11 kilometers. You see it just by going to the y-axis where we have altitude, and here's minus 56.5 degrees Celsius. You just see this by going down to the x-axis. So again, every point on an XY diagram has both an X value, the temperature, and a Y value, in this case, the altitude. And so finally, here is our point for 16 kilometers, and again, the temperature stays at minus 56.5 degrees Celsius. Now, this is something called the standard atmosphere. Now, to get the vertical temperature profile in the standard atmosphere, all you're going to do with a ruler, so again, what I would recommend is you actually open up this diagram. So in the investigations manual, if you just click on the figure, it'll open up the figure in another tab in your browser, and you can just print that. So you can actually draw this on the printed piece of paper, and then what you're going to do with a ruler is you're just going to connect these 3 points. And what you will have created is a standard atmosphere. So what the standard atmosphere shows you is in a standardized, an idealized way, what the vertical temperature profile looks like in the troposphere. This is basically from 0 to 11 kilometers, and then the tropopause from 11 to 16 kilometers. So the standard atmosphere, it's not the real world, and we'll see soon enough before we get to the end of this video that the real world looks a lot more complicated than the standard atmosphere. But the standard atmosphere is a great first cut, an idealization of what the vertical temperature profile is in the troposphere and the lower part of the tropopause. Now, having said that, we're going to take a look at an example in Investigation 2B for Brookhaven, New York. Now, what we're seeing here in Table 2B2 is values of temperature and altitude and pressure that have been measured by a radiosonde that was sent up at Brookhaven. So remember, the radiosonde is that little box of instruments that is attached to the bottom of a weather balloon. So the weather balloon goes up, and as the weather balloon is rising through the troposphere and the tropopause, what it does is it reports pressures, the temperatures at that pressure, and the altitude at which we reach that pressure. So at the Earth's surface at Brookhaven, which by the way is very, very close to sea level, what we see is that the pressure is 1,026 millibars. The temperature is 14.5 below 0 Celsius. This is a very cold day, by the way, in January. 12Z is 7 o'clock in the morning. And this temperature is really just around probably about 10 degrees Fahrenheit, maybe even a little bit colder. It's a cold morning. And you'll see that it is 0.02 kilometers above sea level. Now, as the radiosonde rises and we go up in altitude, you'll see that the pressure always is decreasing. It's always decreasing. So again, pressure or weight always decreases with height. And we'll see in the troposphere that the temperature is pretty much always decreasing with height as well. Now, if you look really carefully, you'll see that between 200 and 150 millibars, the temperature actually goes up a few degrees. It's cold, but the temperature actually goes up a few degrees before it begins to go down again between 150 and 100. So the tropopause, which is not perfect in the real world, the tropopause is probably located somewhere in this 150 to 200 millibar range. And then you can see here are altitudes as we go up. Now, an interesting characteristic about pressure in the atmosphere. As you go up through the atmosphere and the atmosphere's weight decreases, it doesn't decrease in exactly the same way that a person's weight decreases. And what we see, in fact, is that atmospheric pressure or weight decreases very, very rapidly as you move up just from the immediate surface. And the higher up you go in the atmosphere, the slower the rate of that pressure or weight decrease becomes. So, for example, if you take, something just fell in my kitchen, but I'm going to keep on talking. So, if you go up from the surface to 900 millibars, you'll see that you have to go up through just a little bit less than a kilometer of atmosphere for the pressure to have decreased by 126 millibars. So, less than a kilometer. Now, if you go up from 150 to 100 millibars, so a 50 millibar decrease, you go from 13.39 kilometers to 15.99 kilometers, or a distance of 2.6 kilometers. So 1.26 millibars, 126 millibar decrease, you go up less than a kilometer. Just a 50 millibar decrease, you go up more than 2.5 kilometers. So I just want to point out that this is different than people. Our weight decreases relatively uniformly with height from foot to head, but the atmosphere is different that way. All right, now let's keep going on here. So again, here is our Brookhaven. Here's our Brookhaven radiosonde profile of pressure, temperature, and altitude. And you're going to be asked by the AMS in the investigation to plot these points on the Stüve diagram so that you can compare them with the standard atmosphere. Now, I've cheated here a little bit. The AMS may not be happy with me, but I did connect those 3 points in the standard atmosphere right here so you can see what the standard atmosphere looks like. Remember now that what you're looking at is an idealized vertical temperature profile from the Earth's surface through the troposphere and then up through the lower part of the tropopause. All right? Now, when you're given real-world data and you're asked to plot these data on the Stüve diagram, in reality, what you're going to do is you're going to ignore this right-hand y-axis. You're going to ignore altitude. And when we look at real-world Stüves, in fact, there will be no altitude measure on the right-hand side of the diagram. There'll just be pressures on the left-hand y-axis. So when you plot these values onto the Stüve, on top of the Stüve where you already have your standardized atmosphere, you're not going to pay attention to altitude at all. This is just going to go away. You're going to ignore this right-hand column. So you're going to just basically plot based on the pressure value. All right, so just keep that in mind. And when you plot these dots, I recommend that you start at the bottom, that you start at the surface and work your way up as you're plotting these dots. Now, we're not going to do this. We're not going to plot Brookhaven in this video because I'm not going to give this away. The AMS would be very unhappy with me. Instead, what I'm going to do is I'm going to show you an example from a previous year, from a previous investigations manual. So we're going to take a look at radiosonde data from Fort Worth, Texas at 12Z, the 20th of January, 2022. So this is from a couple of years ago. The table looks very similar. So you've got pressure levels, you've got temperatures, and you've got altitudes. All right, so again, pressure always decreases with height. You can see the temperature is pretty much decreasing with height the entire way up, but you'll notice by the time you get to, again, about 200 millibars as you go up, you'll see temperature actually increases a little bit and then decreases a little bit. So you can figure out where the tropopause is probably located here. Again, roughly around 200 millibars, and then here are altitudes. As I said with our Brookhaven example, when you plot these data, and we're going to do it in the next slide, you ignore altitudes. You plot with pressure as your y-axis and temperature as your x-axis. So let's do that. Now I made the table really, really small here, but this is the information from the previous slide. Here's our Stüve diagram with the standard atmosphere still on it, and I'm going to start the surface, and I'm going to just plot the data going up to 500 millibars. Now remember that every dot that you're going to plot has a temperature value and a pressure value, an x value and a y value. So let's plot our surface value at 1,007 millibars. So here's 1,007 millibars, and here's our temperature of minus 2.7 degrees Celsius. Here's 1,000, or 1,007. You just go down to the x-axis, and here's your minus 2.7. Let's plot our 850 millibar dot next. So here's 850 millibars. Here's this horizontal line, this 850 millibars, and you're just going to go along this line until you get to a value of minus 1.1. So it's going to be right about here. There it is, minus 1.1. All right, next one, 700 millibars, and you've got minus 6.3 degrees Celsius. So here's 700 millibars. I'll start over here. I'm going to move right along this horizontal line so we stay at 700 millibars. I'm going to go to minus 6.3, which is going to be right about here. Boom. And I'll do one last one, 500 millibars. So we come up to 500 millibars, stay on this horizontal line. So our horizontal lines are pressures, our vertical lines are temperature. So I'm moving right along the 500 millibar line. I'm going to keep moving along until I get to minus 20.5, which is going to be right about here. Now what I want to make it clear here is that the real world is not the same as the standard atmosphere. In fact, what you see is that at Fort Worth, in the lowest part of the troposphere, we actually have a little bit of a temperature increase. We refer to these layers where the temperature increases with height in the troposphere as inversion layers. We call them inversions because what we see in these layers is the inverse of what we expect. So temperature is actually increasing where we would expect it to decrease. It's the inverse of what we expect. And then invariably, as we continue to go up, temperatures will begin to decrease with height in the troposphere. The other thing that you'll see in the lower part of the troposphere in our Fort Worth example is that Fort Worth is actually colder than the standard atmosphere. So this is probably a fall, or given that the temperature even at the surface is below 32 degrees, this may well be a wintertime example. I can't remember if I gave you the date for this. Did I? I did. It's the 20th of January. So yeah, it's a winter example. And so when you see these winter examples, in this case, the real atmosphere is colder than the standard atmosphere. If I were to give you an example from July or August in Fort Worth, where it's probably closer to 100 degrees, the surface temperature would be out here somewhere, closer to 40 degrees Celsius, and the real atmosphere would be hotter than the standard atmosphere. So just remember, the standard atmosphere is an idealization. It's a model of the real world. Let's go back to Brookhaven. So again, this is table 2B2. Remember that you're going to be plotting Brookhaven in the investigation to answer questions in the investigations manual before you take the quiz. So you're not going to do Fort Worth, you're going to be plotting these values. Now, just moving forward, the last time we're going to take a look at is a real-world Stüve of Brookhaven. And this is what it looks like. This is from 12Z. Here's the 1200 right here. If you take a look at the numbers on the upper left-hand corner, here's the 1200. This 01 is January. This 110 is 10, pardon me. And this 24 is 2024. I am looking at Brookhaven, I hope. So anyway, this is what it looks like. And so what we have here is our temperature. I want to just show you a couple of things. This is a real world Stüve. It's very confusing, very confusing. So what I want you to do is to just kind of filter out some of this stuff in the Stüve. Focus on the grid of vertical and horizontal blue solid lines. The horizontal blue lines are going to be your pressures. just like we've had in what we've looked at so far in the earlier examples. The horizontal blue lines are pressures. Pressure is always going to decrease with height. In our real-world Stüves, from 1,000 all the way to 100, just like we had in our previous examples. The vertical lines are going to be our temperatures, starting with 80 below Celsius, going all the way to 40 above. So basically, if you just focus on the grid of solid blue horizontal and vertical lines, this is what we've seen in our previous examples, like this. So everything else, the diagonal green lines, the dashed blue lines, the dashed brown lines, ignore all of it. Just ignore all of it. And so just focus on the grid of solid blue lines. Now, if we take a look at the two black vertical profiles in this particular example, what we see here, and by the way, I don't think this is from our current investigation. I think this is from a previous investigation still. So this is not Brookhaven. Matter of fact, I'm pretty sure this is Salt Lake City. So that's okay. We can still take a look at what this is telling us. So this vertical profile on the right, for this example, this is the vertical temperature profile for Salt Lake City in this particular example. So you see that the temperatures are decreasing pretty uniformly with height in the troposphere. We get a little bit of wiggliness. We're still in the troposphere here. It's when we get to about, in this example, just about 300 millibars, maybe a little bit higher up, where you can see that we now are getting into a layer of the atmosphere with increasing, decreasing, but on the whole, it's uniform. This is the tropopause. So the tropopause, basically in this example, starts maybe at about 270, 280 millibars, and everything below it is troposphere. But the right-hand profile is temperature. The left-hand profile, which we're really not going to focus on yet in our class, we will eventually, but you can either pay attention to it or ignore it for now. But the left-hand profile is the vertical dew point temperature profile for this example for Salt Lake City. I apologize. I'm not quite sure why I didn't replace this example with the Brookhaven example from our current investigations manual, but I didn't, but it's okay. This basically matches, not in terms of the precise examples, but what it is that's happening with temperature on the right, dew point on the left. And when you take a look, by the way, at the vertical dew point temperature profile, you will not be able to identify the tropopause. You must look at the temperature profile, the right-hand profile, to identify where the tropopause is located. And I guarantee you, in our Brookhaven example, for this investigation, it will be at a different pressure level than our Salt Lake City example that I'm showing here in this particular video. All right, I apologize for not showing the Brookhaven example. I should have done that. I didn't replace last year's Stüve with this year's Stüve, but it's all right. It's okay because it gives you a chance to actually take a look at Brookhaven and compare it to this example as well. When we get later on into the session, further into the session, we will be looking at more real-world Stüve diagrams. So make sure and just study what I've told you to study, our blue grid of horizontal and vertical pressure and temperature lines, and make sure you understand, or at least willing to accept for the time being, that the vertical temperature profile is to the right, the vertical dew point profile is to the left, and that you need to look at the temperature profile to figure out where the troposphere ends and where the tropopause begins. And I'll say one last thing before I end, and that's that we have some wind information right here. And this basically is our wind direction at speed at a bunch of different vertical levels in the atmosphere. Now, to figure out which vertical level it is, you need to take a look at the very end of our wind direction line where our station model circle would be located at the surface, and just go over, and that will give you the pressure level. All right, that is pretty much all I'm going to say about Investigation 2B. A lot of information, some of it a little bit confusing, some of it a little bit conceptually challenging. If you have any questions about anything that I've done here at all, by all means, post questions to the discussion board, or feel free to ask me live during my office hours on Zoom. But that's everything I'm going to say about Investigation 2B. I'm going to end this now. I'll post it on YouTube, and you'll receive announcements from me when it's ready for you to view.